Good afternoon, everyone. Today we have a great honor to welcome the talk by Professor Kip Thone in the title Black Holes and Gravitational Waves. Professor Thorne was the Feynman Professor at California Institute of Technology until 2009. He is one of the world's leading experts on the implications of Einstein's general theory of relativity. He is a very well-known American theoretical physicist, a friend and colleague of Stephen Hawking and Carl Sagan. He has written books on topics in gravitational theory and high-energy astrophysics, and the black hole, the time wrap that many of you have it. So this is time that we will have a great opportunity to listen to the story about black hole from Professor Thorne in person. Please give a warm welcome to Professor Thorne.
Can you hear me in the back easily?
Yes.
If I don't use that, can you still hear me in the back?
Yeah.
Okay, so do you think this is necessary for the recording? Up to me. It would be easier without this, and I do speak rather loudly. Okay, so let me try without. So I'm going to be telling you about very recent research about black holes and current research and near future plans for gravitational wave observations of black holes and other similar objects. But let me begin with some history. When I was a young student, that was the beginning of what is sometimes called the golden age of black hole research, 1963 to 1977. This golden age was driven by observational discoveries, the discovery of quasars and the realization after some years that they are powered by a black hole at the center of an accretion disk, a black hole that can produce jets that power radio sources outside a galaxy. The discovery of compact X-ray sources, again a black hole, pulling gas off of a companion star into an accretion disk. In this case, black holes with masses of millions to billions of solar masses. In that case, black holes with masses between 3 and 100 solar masses. These discoveries motivated theoretical research, and there were a number of major discoveries in that period. We came to understand that black holes are solitons. They are objects made of a field which holds itself together by its own energy. In this case, the field is gravity. Gravity is described in general relativity as a curvature of space-time. So a black hole is an object with strongly curved space-time where the curvature is produced by the energy that is in the curvature through nonlinear self-interactions. We learned that there is a singularity at the center of a black hole, a singularity where, according to classical general relativity, the space-time curvature becomes infinite, but a singularity that in reality will be governed by the laws of quantum gravity from combining quantum physics with relativity. We learned that black holes can be dynamical. They can spin, and when a black hole spins, it drags space into motion around itself, or we say it drags inertial frames, so that if you are very close to the black hole, you are forced by this dragging of space to move around the black hole yourself relative to distant stars. And it's impossible to avoid being dragged around, rather like a straw in a tornado being dragged around. We learned that black holes can vibrate They can vibrate, changing shape like this. Stephen Hawking combined quantum physics with general relativity to predict the existence of Hawking radiation, which can be thought of as due to pair production by gravity in the vicinity of the horizon of the black hole, with one of the particles going into the hole and the other escaping. This motivated an understanding of the thermodynamics of black holes. At that point, about 1977, this subject got split into two pieces: the theory of classical astrophysical black holes and the theory of quantum black holes. In a very recent issue of Science magazine, about 2 weeks ago, there is an entire issue devoted to black holes, and at the beginning there is a survey of classical black holes, which I wrote, a survey of quantum black holes written by Ed Whitson. This is an interesting volume to look at. Today I will talk only about classical astrophysical black holes. I will not discuss these quantum properties of black holes. By 2009, we understood a large amount theoretically about quiescent black holes. That is, black holes that either are just spinning and interacting with their environment, or perhaps vibrating with a small amplitude, but no large motions. We understood them theoretically very well. We had only a small amount of observational data about them. The data we have describe how a black hole interacts with its environment to produce jets and produce the X-rays that are seen from, for example, from Cygnus X1. But the observational data tell us very little about the black hole itself. The optical data are just beginning to verify that these black holes are spinning, for example. No accurate measurements of their spins, and no observations of the detailed space-time geometry of the black hole. And highly dynamical black holes, we have had by 2009 essentially no understanding of them, and absolutely no observations. No understanding except for some very important theorems. Penrose's theorem that says that there is a singularity at the center, and Hawking's theorem that says that black holes' surface areas must increase no matter what happens. But that's all we know about highly dynamical black holes. The most interesting situation in nature where we get highly dynamical black holes is when two black holes orbit around each other in a binary, spiral together and collide and create large amplitude oscillations of the geometry of space and time. So the status back in 2009 or 2006, in the mid to late 2000s, was with black holes, it was as though we had seen the surface of the ocean on a very calm day, but we had never seen the ocean in a storm. We had never seen breaking ocean waves. We had never seen water spouts. And we want to understand curved space-time in a storm. How does it behave in a storm? How does it behave when it's strongly excited? And the place where we can most readily study this, both observationally and theoretically, is in black hole collisions. And so this has been my principal direction of research for the last 10 years. The study of these large amplitude oscillations of curved space-time, that is, nonlinear dynamics of curved space-time, is also called geometrodynamics. This is a word coined by John Wheeler, who was my PhD thesis advisor half a century ago. We, in fact, are at the beginning of a new golden age of research in which we are beginning to study geometrodynamics. And we are doing it through observing in computer simulations and soon in the future through gravitational wave observations, observing the collisions of spinning black holes. This new golden age is being driven by numerical simulations of the colliding black holes. There are a dozen research teams in the US, Canada, and Europe doing this. And it's being driven by observations, or the prospect for observations of colliding black holes using gravitational waves. So I will talk in this lecture about both of these subjects. And let me say I would prefer to have discussion during the lecture. I would be pleased if you interrupt me and ask me questions. Yes.
Besides detecting the gravitational waves, can we use the technique that we're taking from the gravitational lensing to try to get these kind of phenomena?
So the question is, besides gravitational waves, can we also study these kinds of phenomena through gravitational lensing? And the answer is not very well through the usual type of gravitational lensing, because the black holes are very small and our angular resolution is not good enough to see close to the black hole with gravitational lensing. We can see down to angular scales with gravitational lensing as small as a milliarc second. But we need things at microarc seconds or nanoarc seconds. And so we can see some properties of black holes, but not much. So the only way to study the black holes in detail, to study their warped, their curved space-time, I believe, is gravitational waves. There is some hope with radio waves. If you have a neutron star orbiting around a black hole, the SKA may be able to observe the radio waves as the neutron star orbits around and spirals toward the black hole. So that is the one other possibility in the near future. So I will talk then first about numerical simulations. These have been under development since the 1960s, the same as gravitational wave detectors, in fact. But there has been big success only in the past several years. So how are these numerical simulations done? The task is to evolve the geometry of space-time instead of evolving fields in space that live in space-time. So in computational fluid mechanics, for example, you study the evolution of fluids that live in space-time. In numerical relativity, you study the evolution of the space-time geometry itself. To do this, you choose an initial space-like three-dimensional surface in space-time, the analog in curved space-time of a slice of constant time in some inertial reference frame. In special relativity, you have many different inertial reference frames. Similarly, here you have many different ways to choose an initial three-dimensional surface. You then put coordinates, you put spatial coordinates on this surface, this three-dimensional surface. You specify, as a function of location in the coordinate grid, the three-dimensional metric that describes the geometry of this surface. And you specify something called the extrinsic curvature, which is approximately the same as the first time derivative of the three-dimensional metric. You cannot specify these freely. Just as in electromagnetism, you can specify an initial magnetic field, an initial electric field, but only subject to constraints that the divergence of the magnetic field vanish, for example. There are similarly constraints in Einstein's theory on what you specify for the metric and the extrinsic curvature. after you have solved these constraint equations to get the initial conditions, you then have to lay out coordinates going toward the future. And you do this by specifying something called the lapse function that tells you how rapidly you move your coordinates forward, and something called the shift function, which tells you how you adjust your coordinates spatially as you go forward. This is the most technical slide in this talk, so bear with me. You then integrate the three-dimensional metric and the extrinsic curvature forward in time using Einstein's dynamical equations. And finally, you construct a full metric of all of space-time from the lapse function that you've specified in the shift function and the evolving three-dimensional metric. So that just gives you some sense of what's involved in numerical relativity. There are two mature approaches to numerical relativity. The first uses finite difference description of the spatial geometry. So you give the values of the metric coefficients at different locations, at discrete locations in the coordinate grid. The second method is a spectral description in which you divide space up into cells. You have one black hole here, the other one there. You divide the space up into cells, into little three-dimensional domains, and in each cell you expand in basis functions. Maybe a Fourier series, or it may be an expansion in some other orthogonal polynomials. Then you evolve forward the expansion coefficients. Each cell is evolved forward using one CPU of a computer cluster. And the computer cluster, the CPUs talk to each other, exchanging data across the boundaries. This is a much more complicated method than finite difference methods. And as a result, it was much slower to reach maturity. But its advantage is that when there are no shocks, when the things you're evolving are smooth, the solution that you're building converges exponentially rapidly as you make your grid finer or as you use more basis functions. And this exponential convergence means you can get very high accuracy with far smaller computational resources using this method than the finite difference method. But it's a much more complicated, it's much harder to make this work. Today, these are most of the groups that are simulating black hole collisions. Only one team is using the spectral methods, and that's the team that I am associated with. It's my team. Cornell, Caltech, the Canadian Institute of Theoretical Astrophysics, and also, more recently, Washington State University. The spiritual father of this group is Saul Tucholsky, who is the Hans Bethe professor at Cornell, and I guess I'm the spiritual godfather of this group. I don't do the simulations myself, but I'm very much involved in getting the science out of the simulations and in motivating the simulations and in raising the money to support what is basically a $2 million a year research team. So let me describe what we have learned. Let's begin with these black hole collisions. Black hole collisions are the most violent events in the universe. When two spinning black holes orbit around each other and collide, let me just back up and describe physically what goes on. Each black hole drags space into motion around itself like the air in a tornado. So you have two tornadoes of spinning space, whirling space. The orbital angular momentum also drags space into motion. So you have two tornadoes embedded in a third larger tornado. They come spiraling together and collide. And you want to know what happens when the tornadoes are made from curved spinning space and not made from air. And in this process, it turns out that about 10% of the black hole's mass is converted into gravitational radiation. You might ask, how do we define the mass of a black hole? The answer is, imagine putting a planet in orbit around the black hole and apply Kepler's laws. That's the way we measure the mass of the Earth, is through the motion of the moon. That's the way we measure the mass of the sun, through the motion of the planets around the sun. And in relativity, that mass defined in that way obeys a conservation law. And it says that when two black holes collide and merge, if the final mass will be about 10% less than the sum of the initial masses. And that has to come off in the real physical energy by the conservation law. It comes off in energy carried by gravitational waves. And 10% efficiency is enormous. Compare that with nuclear fusion, which is less than 1 part in 200, from burning from hydrogen all the way to iron 56, the most tightly bound atomic nucleus. During the collision, all of this energy, most of this energy comes off in a time that is about 100 times the time it takes light to travel across what we call the Schwarzschild radius, across a distance of order the size of the black hole. That's 100 Newton's gravitation constant, the mass of this binary divided by the speed of light q. So you notice that the energy that comes off is proportional to the mass. The time that it takes for the energy to come off is proportional to the mass. So the power output during the collision is about 10 to the minus 3 c squared, the speed of light squared, divided by Newton's gravitation constant. Yes?
Sorry, will we observe the same effect for the collision between stellar mass black holes and the supermassive black hole?
Excellent question. So will we see the same effect for supermassive black holes of, say, 1 billion solar masses, and stellar mass black holes of, say, 10 solar masses? The answer is absolutely yes. It scales with the mass. The energy that comes off will be 100 million times larger for the supermassive black holes. It will come off 100 million times more slowly. And the power output during the collision will be independent of the mass, the same for stellar mass and for supermassive black holes. This number works out to be 10 to the 24 solar luminosities. That's 10,000 times the luminosity of all the stars in the universe put together. 10,000 universe luminosities from two black holes colliding. For stellar mass black holes, this comes off quickly in a time of about 1/10 of a second or 100th of a second. For supermassive black holes, it comes off in a time of a day, roughly. But during the collision, the luminosity is 10 to the 4 universe luminosities. But that's impressive. And no electromagnetic waves. It's all gravitational waves except, and this is important, black holes are typically surrounded by accretion disks of hot matter. And when the two black holes collide and merge, they will strongly disturb the accretion disks, and astronomers will be able to see the electromagnetic emission from the accretion disks being disturbed. I will return to this near the end of the lecture. The details of the collision, in fact, are encoded in the shapes of the gravitational waves, what we call the waveforms, like the waveform on an oscilloscope for a sound wave. So the I told you that for the past 10 years I have been working on this problem of studying geometric dynamics. This is my principal research. For the preceding 20 years I was focused on initiating gravitational wave detection by laser interferometer gravity wave detectors. And I will talk then in the last part of my lecture about observing these waveforms and extracting from the waveforms that will be seen by the kinds of detectors that my colleagues are working with, extracting from the waveform detailed information about geometric dynamics. Now, how do we visualize geometric dynamics? I don't want to use equations or numbers. The problem with the simulations is in a simulation you come out with 10 to the 9 bits of information or more. Okay? And you don't know how to understand them. And the only way to really understand them is visually, through a visualization. So the way in which we visualize what is happening until recently is the following. We would build something like a so-called embedding diagram of the colliding black holes. We would build a shape here that describes part of the three-dimensional geometry. It looks like a funnel. What we actually plot here in terms of height is the so-called scalar curvature associated with the three-dimensional metric. So it's just plotting one parameter out of 6 components here. And then we use color coding to display the lapse function. That is the slowing down of time as you approach the horizon. The horizon of the black hole is down here. Time is flowing very slowly down here, much more rapidly up there. So in the red regions is a slowing of time. Then the shift function, which you can think of as the dragging of space into motion, is shown by these arrows. So I will show you a movie of a very boring black hole collision. 2 identical black holes that are not spinning. This is a movie by the team that I work with at Caltech, Cornell, and CETA. You're going to see 3 different things in the movie. Here you see the 2 black holes as they would appear against a dark blue sky. Here you see this so-called colored embedding diagram for the shape of space of the black holes, the dragging of space into motion with the arrows, and the color coding for the slowing of time. Down here you see the gravitational waveform. I'll talk about these waveforms later, for the shape of the waves that are being emitted in this process. And let me just move this out of the way. And so let's let this movie go. So you see the 2 black holes going around each other as you would see them against the blue sky. You see them as they would be seen by an observer looking in from outside our universe to see the warping of space and time. You see the waveform. It got boring, so I jumped way over to here, and then we will watch the black holes collide and merge. Pause the movie so you can admire the collision. And then the black holes begin to vibrate and settle down into a final state. Now, there's a problem with this kind of way of describing the results of the simulation. Too little of the space-time curvature is depicted in this way. For example, you do not see the gravitational waves because they are in a piece of the three-dimensional metric that is not part of this scalar curvature. So the most interesting thing you don't even see in these pictures.